Warm welcome to everyone in this week's Data Science e-meetup hosted by Erium. Today we have Dr. Sebastiaan van Zelst as a guest, and we will discuss process mining. We had an e-meetup already quite a couple of months ago on the topic, but it was given by a not so experienced speaker on the topic, namely me. But nevertheless, the topic was requested. We had some touch points in the past, but not comparable my experience with process mining compared to Sebastiaan. He's one of the founders of PM4Pi, and I'm very looking forward to the content that you prepared. And having said that, please go ahead with your presentation. And to the audience, please feel free to ask questions anytime. That's the rule of the e-meetup, or put the questions in the chat. Sebastiaan, the stage is yours.
Yeah, Theo, thank you very much. Can you hear me, by the way? Is the microphone good? Okay, perfect. I will try to monitor the chat, and as said, just interrupt me, and I hope that I can live up to the expectation. Maybe your presentation was already so good that in the end I'm not telling anything new. Could be, we will see.
Disclaimer, no, it will be new stuff today.
Okay, so let's kick off. Let me first briefly talk about myself before we go into the process mining quote beyond the hype talk of today. So a little bit about myself and my background. Even though this is a bit of a meeting in a let's say German constellation, and I do speak German nowadays, I prefer to talk about my subject in English. And also this is because I'm not from Germany, I'm from the beautiful Netherlands, and I know at least one person is also in the audience that's from the Netherlands. I did my bachelor's in computer science in a Technical University of Eindhoven, then did my master's there in business information systems, studying architectural design of information systems, and then I decided to do a PhD in the, back in the day, not so commonly known area of process mining. Actually, in between my master's and PhD, I briefly worked as a software engineer in industry, but wanted to still do a PhD because I had the feeling at the time that in my point in my life, that was something to be easily done when I was in my early 20s, and would be more difficult to do it later. So yeah, I did my PhD actually on online real-time process mining, so using real-time data and online data streams in process mining. And at some point I graduated and then became a senior researcher in Fraunhofer FIT. We are affiliated with the research group that is headed by Professor van der Aalst, which is often referred to as the founding father of the process mining field, one of the main initiators behind the whole field. I also do a lot of research together with him. And nowadays I'm actually heading a research group within Fraunhofer myself, and also deputy head of the whole data science department. And yeah, what the future will bring, you never know, right? We don't have a crystal ball. Although also in process mining, sometimes we would like to have a crystal ball to predict what's going to happen next in the process. So having said that, it's a nice bridge to process mining. And whenever I give a talk, I would always want to try to sketch to you very in a clear, intuitive manner what, for people often working in process mining, what the process actually is, and based on that to explain what process mining is. So, and I always use the example when I explain process mining, specifically when I explain how we look at processes, I always use the example of the morning routine that we all execute. So this is a process we all execute, and I try to use this example to sketch how we look at processes when we talk about process mining. So what did I do this morning, and what do I often do in the morning? The hardest part is always that to wake up. So my alarm clock rings, and nowadays I have a beautiful young daughter that often acts as a replacement of this alarm clock here. And then after that the alarm clock has rang and I decide to wake up, I take a shower, put on some clothes, have breakfast, brush my teeth, and I go to work. So what we see in this slide is a bunch of activities. And these activities have also some things in common. For example, most of these activities they take some time. So waking up takes a bit of time, having breakfast takes time, taking a shower takes, oh my God.
Interesting. So let's hope that the oh my God was not Godzilla.
That's exciting.
Let's hope it was just like the laptop running out of battery. I actually had it in the past, so giving a talk virtually, and my talk was half an hour, and I completed my talk, and then 15 minutes later, or like half an hour later, I don't remember the exact number of minutes, but like short, we had a power outage, and everything was offline. So this was the time when I then hook up my router to a USP. UPS, uninterruptible power supply.
It was a virtual meeting as well.
Yeah, it was virtual. And I was like just doing it here at home, had the Erium banners behind me. So everything looked official, but it was just like here at the home office.
But at that time you didn't expect it. So probably you weren't like, oh my God, before you fell out.
Yeah, right. And it was like the first and only time in this house since we live here that we had a power outage. Yeah. But it was lucky. I was lucky.
Yeah, it happens. It's also a drawback of the whole hybrid and digital thing. Yeah.
Definitely. Okay, and I got an email. My laptop decided to reboot. Back in a second. All right. But actually, like the home office here, it kind of turned into like a little studio because we also produced the Erium podcast. So I've got all the equipment here, like professional microphone stuff.
Oh wow! Yeah.
So this even binds me to the home office. So I don't. I'm not able to do a recording in the office actually because all the hardware is here.
Yeah, it's actually that your home office becomes more comfortable than the actual office.
Yeah, but I have to say, like the coffee machine we have in the office,
it's better.
I could not afford like this coffee machine for at home, not yet. So maybe I have to sell my first startup for that.
Still in your country, it is work from home.
We've most of the time work from home. Yes, so we have like one fixed office day now. We introduced it one, but yeah, turned out to be quite easy to coordinate meetings online. And we have like now team members in the Erium team working from somewhere on the planet, even like colleagues from Vienna, Singapore, then colleague of us worked for like, I think it was 3 months from New York. Then time zones kick in. Yeah, this we realized. But yeah, having the meetings online is not a problem.
Yeah, that's true. Now we are used to it.
Exactly.
So I'm back. I'm sorry about that. It's when you have an IT department managing the software on your PC, and
No
you are
problem.
in the network. Now I'm out of the VPN, so I shouldn't be again triggered to reboot. Okay.
No worries. Told some stories about the good old times, so you can just go ahead.
Okay. Okay, perfect. So yeah, as I was saying, what I do in the morning is I'm executing these activities. They have some duration. And what's also interesting, and it's also very important to realize, is that this is a set of activities that I perform multiple times. So there's some notion of repetition actually in this, right? It's not something that I do one-off. No, I do this actually every single day. This is an important factor to take into account, that in process mining in general, what we aim to analyze is processes that have some, let's say, some form of repetition inside in terms of their execution. That actually makes us able to also improve those processes. But there's more to this picture. So if you look a bit closer, we see that among these different activities, there are certain relationships. Like, for example, you would typically take your breakfast before you brush your teeth, and you typically take a shower before you put on some clothes. You do all of this after you wake up, and you do all of this before you go to work. Now, some of these things you can theoretically do completely at the same time. There's no one that sort of would restrict you from taking your breakfast while having a shower. It's not necessarily, let's say, the easiest or most comfortable thing to do, but it's not something that theoretically is impossible. And the same actually holds for brushing your teeth. So on the one hand, you see there are certain relationships among these different activities, certain ordering relationships, as these relationships are called. And at the same time, there's the possibility to do certain things in parallel or concurrently, so at the same time. So that's the process side of process mining. And if you would like to quantify that in a more generic way, you could argue a process that we often consider in process mining, though it's not necessarily limited to this definition, but typically we look at a collection of activities that an organization executes, more often than once, so a repeated set of execution. This execution is supported by resources, which are either human or machines, can be digital, can also be physical machines that from mechanical engineering domain. And in the end, the goal is to execute this collection of activities where there are some ordering relations among these different activities to achieve a business goal. And these business goals, they vary among the different possible application domains. So to give you some examples of processes, or let's say of phenomena that you can think of along the lines of this definition of a process. So for example, if you think of logistics, in the end, what postal companies do or what logistics operators do often is they move stuff, they move goods from A to B. And to move these different goods from A to B, the logistic operator will perform a bunch of activities with respect to the goods that they are handling to do so. So a set of activities performed by different types of resources. Parts of logistic chains are these days completely automated, and other parts are still done by human employees, as an example. Of course, the business goal here is to get the goods that are being shipped to, let's say, the receiving party as fast as we can, or with a, let's say, nowadays also the ecological footprint of such a process is of high importance. The financial domain is a different branch where processes play a fundamental role. For example, if you want to buy a house, you require a mortgage. To get the mortgage, the bank will trigger a large set of actions or activities in order to determine in the end whether or not you are allowed to get the mortgage. And they will take a lot of factors into account in doing so. So you could think of this, the business goal here would be to decide whether I can get the loan or not of a certain amount of money. And the actions are performed by the banking system, but also by employees. Some reviews might need to be done, etc. Some documents need to be collected, etc. Of course, the medical domain, clearly we have the goal to heal a patient, or if that is not possible, to make the final part of someone's life as, let's say, pain-free as possible. And you can also think of online shopping, where in a way the customers are actually executing some form of process, because a lot of people will do a lot of similar sequence of actions in your online shop, but also the whole chain in a way can be seen as a process. So what I'm trying to sketch here is that this concept of collections of activities that we perform on to achieve a goal is something that's omnipresent and applies to a lot of different, let's say, branches. Now, what's the fundamental difference between my example process that I used initially, that is my morning routine, and the processes that I'm showing in this specific slide, is that the notion of a logbook. So what most of us, I guess, don't do is we don't write down on a piece of paper every morning at what point in time we have done which activity. And we also don't have any recording of how much time it takes, right? So we're not really aware whether we on average shower 5, 10, or 15 minutes. So there's no tangible recording, no tangible data, whether that's on a piece of paper or in a digital tabular form, doesn't really matter so much. There is no historical proof that if I would tell you what I do in the morning, it's actually also what I really did in the morning. There's no tangible asset that allows us to verify, historically speaking, whether what I'm telling you is correct. But this is different for these example processes that I've sketched. So for all these different example processes in all these different domains, these organizations, they rely on all kinds of information systems ranging from these ERP systems such as SAP or Oracle to manufacturing execution systems, which are often called MES systems, customer relationship management, CRM systems, Salesforce, these types of systems. They support these organizations in executing these processes. And often you see that in this support also actually these systems store digital traces, digital footprints of historical behavior in the underlying databases that underpin these information systems. So there is, in fact, for these processes, there is some tangible, although it's digital, but there's some historical information, some historical sources of information that we can actually exploit to get a better understanding of what happened, historically speaking, in our processes. Now, that's the whole process side of process mining. There's processes we execute that generates some data that we can try to analyze, and obviously the mining part, like in data mining, is actually some sort of equivalent to what these guys are doing here in this mine, where they have a machine that they use to extract valuable minerals or out of this raw rock. So obviously in this analogy, the data is the rock. The machine would be software that is capable of analyzing the data, and the guy operating the machine would be a data scientist. Nowadays, there's people that call themselves process scientists or any business analyst, anyone that is able to take a data set, use software that can analyze this data set and generate meaningful value out of it. That's obviously the mining side. So how I typically like to define process mining is more, I would say, philosophically driven rather than purely technically driven. So I look at process mining, but then again, this is my personal understanding of the field, is the art of obtaining knowledge of and insights into the execution of processes and the processes themselves by means of trying to analyze the event data that's generated during the execution of the process. So for me, it's all about trying to understand processes better by exploiting event data for this purpose. And for me, whatever you do with the event data to some degree is part of process mining. And of course, there are certain standardized means to do that, but I would say creativity should be also exploited as its fullest. So what's important are things like knowledge and insights on the one hand, and on the other hand, we have the analysis of event data. And in the end, everything we want to do revolves around, historical executions of processes. So let's focus a bit more on this event data. So how does this event data look? And to do this, I'm going to use an example. Let's assume that we all co-own a shop. So we have a shop and we are in the gift wrapping business. And our business is basically, we get orders from all kinds of gifts that we have in stock, and we just put them in a box, make sure that nothing breaks, and then ship it to our client. And if you look at the information system that supports our shared company, we actually observe that if you look at it from a bit of a simplified manner, we can extract event data tables that look like this. And normally I'm not a fan of using, detailed examples, although I will actually go a bit deeper in one of the algorithms in a bit later. But this is so simplistic that you don't need a lot of time to get what's going on. So in the end, these data tables that are there in these information systems, they consist of 3 core columns that you need to do process mining with the existing algorithmic tool set nowadays. You need something that allows you to identify, in this example, the order. So that is let's say, some sort of glue that allows us to determine which things have happened in the context of which client, which order, which patient, etc. So you need some ID that allows you to identify these historical activities, they belong together. The second column is, of course, this activity column that represents us, okay, what happened in the past. And the third column is a timestamp column that tells us at what point in time it happened. And what's important to note is that in such a table, there will be multiple rows, and I've highlighted an example here that have the same order ID in this case, where we're handling our orders in our information system. And what's very important to realize is that this allows us to sort of see a historical sequence of events that happened. So for example, for some order in our information system that was internally registered with the number 123, you observe that first, 24th of March this year, an order creation activity, so the order was created in this information system. And then slightly later, roughly 30 minutes later, you see that in the second highlighted row at the bottom, you see an item was added for this specific order, and then the order was submitted to our warehouse. So that's not the complete execution sequence of this specific instance of our ordering process, but it is an example of a fragment of such a process. And if you look closely, there's also an example of an order with ID 124. And there you see the order was created at 5:43, and only 2 minutes later, the item was already added. So for that different order, you see there's, for example, a difference in the time between the order creation and adding the item. Because for order 123, we observed that was roughly half an hour. And for the order with order ID 124, we see that after 2 minutes, an item is already added to the create order. And obviously, if you would have thousands of examples, you could already compute various interesting statistics about the average time between two activities. And you can also match that with your expectations or even with your KPIs that you have on those relationships. So that's the data side. It's really easy. I can basically explain to you in roughly 5 minutes. Let's talk a bit more about the knowledge and insight generation side. And I'm going to do that along the lines of, let's say, predefined categories of algorithms. And I will focus in one specific category a bit deeper. However, in general, note that, as I said, I still believe that anything that helps you get insights in processes where you exploit event data is a form of process mining. And you should also not limit yourself, by the way, only to data. It's usually worthwhile to also talk to people that work in the organization that actually execute the process. The data is just one viewpoint. Anyway, within process mining, we generally observe three main algorithmic pillars to be there. So we have, on the one hand, process discovery, we have conformance checking, and we have process enhancement. I will give analogies and examples for each category, but I will primarily go deep in process discovery. I'm going to sketch to you how, let's say, one of the state-of-the-art process discovery algorithms works. And I'm going to try to do that in a nutshell in roughly 10 minutes. And I hopefully manage in that time. So first of all, let's focus on process discovery. An analogy for process discovery would be the following thing. Assume that you get into a helicopter. So you get into a helicopter, you fly above a certain city, and you make a picture of what you see below, right? So this snapshot here, obviously I took it from Google Maps, but just imagine I took it from a helicopter. So I have this picture, and that's kind of the equivalence of our event data, or what we also often refer to as our event log, this large table that I've shown you before. Now, what we want to do in process discovery, we aim actually to translate this picture into a model, a process model. And this model is intended, like any model, to represent reality. And like any model, process model is also going to abstract from certain details that you would see in reality, but you cannot see that in the model. So that's why it's a nice analogy. Like in this example, you see certain roads have a different color. That's some sort of specialization. You could say these are the highways, or these are more important roads. You can, of course, do something similar when you translate event log into process models. You can, for example, decide to ignore certain roads because they're not relevant for this viewpoint. But there's also other things that you need to sort of keep in the back of your mind when you look at this comparison. For example, if you would take a look at your image that you took from the sky, you cannot look inside of the buildings that are there, right? You can only see the surface of the buildings. And the same holds for event data. So you'll see in event data, you'll see all kinds of information about all kinds of resources, executing activities. But what you cannot really do is you cannot see inside of the minds of these resources. You cannot see if a machine is malfunctioning. Sometimes it's even the case that the resources that perform the worst in terms of time performance are actually your best resources. So a good example of this is brain surgeons. So brain surgeons are, one of the most complex things to do. Hence, all the medical procedures that the brain surgeon operates are going to take an insane amount of time. So you cannot always see that from the data. So you could derive from your data that some resources seems to be underperforming, but that does not necessarily mean that this is a bad thing. So what I'm trying to say is, like picture is a snapshot in time of reality, so is an event log, and it will not always show everything that was in the real world. Anyway, translating that into our example. So if we would take the example event log that I've shown you before, and we would have not just this number of rows, but we would have thousands of rows, and we would feed that into an automated process discovery algorithm, the model we would get is the model on the bottom. Now, what does this model tell us about our warehouse, our process in our shop, the shop that we co-own? Let's zoom in a bit. So based on the data that I, of course, synthetically generated in this example, based on the data, what we observe is that every single order in our system will always first be created. Well, that's nice, but it's good to know. But after that, we see that always at least one item is added, potentially much more items, and certain items can also be removed. However, this construct already tells me that I can never add remove more items than I've added into my order. And that's also, of course, from a compliance perspective, very useful. And then finally, at some point, we submit the order into our warehouse. That's what this first part of the model tells us. So that would be completely derived on the basis of example historical behavioral recordings. If you take a look at the right side of this model, what we observe is we see a large block. And the block is separated by means of a dashed line in the middle. And this block in this specific modeling formalism that I've chosen represents concurrent behavior. And what we observe there is that the invoicing and sending of reminders, which is obviously an administrative side of our process, is done completely concurrently with our stock and warehouse related activities at that part of the process. So I can send invoices and reminders, multiple reminders, or I can not send reminders at all. And I can do that completely at the same time where other people of our organization are checking the stock for the order, potentially ordering goods if required, and finally packing the order. That's what the discovery algorithm is able to decide. And then finally, either we see a cancellation or a dispatch to the logistic service of our company and a closure of the order in the system. Now I'm going to do a deep dive into how such a discovery algorithm works. I'm not going to give the full formalizations, but I will try to sketch what's going on. This you should ignore if you're not into mathematics. But what it basically says, and you can see that on the right-hand side, is I can look at an event log as sequences of activities. And I have decided in this example to just write, I don't really care now about creating an order, sending a dispatch. I would say in this example, creation of an order, I will always refer to that as the letter A. And I don't know, sending goods is letter B. So I'm just using letters as a form of abstraction to make it more easy for me to compactly write about event data. So rather than showing you a table, I have here an event log that captures that there are 5 executions of the process that follow the sequence A, B, C, D. Where A, B, C, D can, again, they just represent some activities. I'm abstracting away from that. And I have 4 activities that, 4 traces, 4 executions that represent A, C, B, D. And then finally, there were 7 executions of the process that started with A, then had activity E in between, and finally D. Again, A, B, C, D, they're just placeholders for activities. Now, I'm going to basically say, okay, the activities in this event log are the activities that I show on the right, A, B, C, D, E. That is the alphabet of this event log. Those are the activities that play a role in the event. Now I'm going to define what we call a relationship between these activities. I'm going to define a relationship that's going to tell us which activity can be directly followed by which other activity in the process. That looks very cryptic, but it's actually very simple. Why? I'm just going to walk through the event log. Maybe I can actually show that with a laser pointer or a pen, even better. I'm just going to walk through the event log to each trace in isolation, right? So these are different traces. I'm starting at the beginning. I'm going to check which activity is followed directly by which other activity. And I observe in my first execution that activity A is directly followed by activity B. And the only thing I'm doing is I'm saying, okay, A is directly followed by B. So I'm going to list that here in this collection. Then I observe that activity B, so I'm just going to keep on walking literally through this trace, and I observe that activity B is directly followed by activity C. And I do that again, so I keep on walking, and I see activity C is directly followed by activity D. Then, okay, so this first trace is now, I've analyzed that. Of course, it happened 5 times, but that's for this initial analysis not relevant. I have basically written down all the ordering relations that I observe in this event log for this trace ABCD. And I'm going to do the same for ACBD. So if I walk through ACBD, I see the first pair of activities that directly follow each other is A is directly followed by C. Then I see that C is directly followed by B. And I see that B is directly followed by D, right? So I'm walking through this event data, and this is what I record. So these 3 relations, they belong to the second trace. And now I'm done processing the second execution. The final execution, AED, the same tricks apply. AE, so A is directly followed by E, so I put it there, and E is directly followed by D. I put it there. And these 2 belong to the final execution. So now I've processed my full event log, and I've listed all the pairs of activities that directly precede each other. A directly precedes B in the first trace. B directly precedes C in the first trace. A does not directly precede D in the first trace, for example, because B and C are in between. Then I'm going to record the start activities. Those are all the activities that start a trace. That is actually only the activity A in this example. And I'm going to do the same for the end, or the final activity. So it's fun to see that on the right-hand side, you see actually how easy this actually is. When you have an example, on the left-hand side, you see what the mathematical equivalent would be. And then what I do is I'm going to create a graph. But essentially what I'm doing is I'm going to create nodes where every activity that I've seen in the process, so that's actually this set AL1, A, B, C, D, E, each member of this collection will become a node. And I'm just going to connect these nodes by means of a directed arc if in this relationship that I've just explained, that it exists. So I'm going to connect A with B because A is directly preceding B. I'm also going to connect B with C because B is directly preceding C. I'm going to connect C with D because C is directly preceding D. So all these, what we call tuples or pairs in this collection, are basically directly translated into arcs in this graph. And there's a little bit of syntactic sugar on top. What I'm also going to do, and I'm just finalizing this beautiful mapping here, I'm going to explicitly keep track in this graph, and that's not really what a graph theory is actually really specifying, but I'm going to specify which activity starts and which activity, or potentially more activities can also start and end potentially any of execution of the process. And I'm doing that by means of these 2 half arcs. So if you have a node that has just a random arc incoming, but there's no other node attached to that, then you know, that is a start activity. And equivalently or symmetrically for the end activities. You have an arc that goes out into the air. So this is actually what we call the directly follows relation or directly follows graph. And it's actually interesting to observe that most commercial process mining algorithms, when they show you an image, they show you this thing, actually. So this is how they compute them. And of course, you can filter those. But now if you want to translate this into a process model, a way to do that is you can look at this, this structure, and you can try to reverse engineer the behavior. So you can try to say, can I detect certain patterns that have to be generated by a certain fragment? What do I mean with that? I can observe here that activity A is always directly in front of B and C and E. And once, so basically I can cut. And once I decide, so you can think this as a border or a line, that once you cross the line, you can never go back, right? If I exit A, I can never get back into A. And for B, C, and E, this exact same relationship holds with D. So when you exit B, when you exit C, or when you exit E, you hit D, and you can never go back. And what this tells us is that there's a sequential relationship between A, something with B and C and E, some type of behavior with B, C, and E, but that's a bit more complex, so I don't know exactly. And finally, D. And we have a mechanism in process mining to capture this, exactly this behavior. We can do that in what we call a mathematical tree with an additional control flow syntax on the internal operators. Long story short, I'm going to represent it as follows. I'm going to draw an arc from left to right, and I'm going to connect activities that I've seen in the same order. So I start with A, that's why it's on the left. Then I have some stuff with B, C, and E, which I haven't completely figured out yet, and I will always finish with D. And what I'm now going to do is I'm going to hide away activities A and D, because I've handled activities A and D. I'm going to focus on activities B, C, and E, and I'm going to try to see in the same graph that I've created, can I find a similar construct for B, C, and E? And when we focus here, you actually observe that when we enter B or C, we can go from B to C and vice versa, and then finally leave. But we can never reach E from B nor C. The same holds the other way around. If I enter E, I can leave also E, but I leave to D. I can never go from E to B nor C. And for when you think again about, okay, which type of behavior can generate this pattern, you realize this is an exclusive choice. So this is an exclusive choice between E and something with B and C. And that means we can cut there and we can say this is an exclusive choice. You either do E and something with B or C. And in this structure, we would represent that by means of this circle with the cross in between. So we now have observed that we first do A, we then have a choice between some stuff with B and C, or E, exclusive choice, finalizing with D. So we again apply the same procedure, but now on the subgraph formed by nodes B, C. And if we do that, we actually observe that B and C can occur in any order. And this tells us, hey, this was actually generated by what we call a concurrent construct. Something can happen in arbitrary order, implies there's concurrency. So then we would cut there, and we would finally end up with the model that you see on the left. And if you're into advanced process modeling, you might see the model on the right, which is the exact same behavior in terms of a Petri net. So that was actually the inductive miner, a bit simplified in roughly 10 minutes. And of course, what you can do is you can associate the number of occurrences of these different relationships on top of this graph and then filter. And actually, that's also what most commercial tools do. So if you play with a commercial process mining tool and you start filtering the paths, they will actually, or even activities, they will actually exploit this frequency information to some way simplify them. That was process discovery. Now let's focus on conformance checking. I will not go so deep, and I also had to go fast a bit, of course, for the sake of time, so I hope it was still somewhat clear. Let's focus on conformance checking, where the best analogy is the analogy that you see here, which I didn't come up with, by the way, but it's still a great analogy. That's performance checking is all about assessing whether a model that is representing the expected behavior of the process, whether that model is actually, if you then look at the data, whether the process is really behaving according to that model. All right. And clearly what you can see here, for example, is there's a model that dictates, okay, reality should go like this. Namely, you shouldn't bike here. But somehow people found a way to circumvent this. And you can see these type of things in data. So you can see things that happen that are not supposed to happen, or you can see the opposite. You can see that certain things are not happening, whereas they were supposed to happen. In the context, again, of our example, and I hope you still remember that we were co-owning a shop and we were sending gifts to our clients. And let's assume that the model on the bottom, which I discovered, is actually also how we want the process to behave. So it's a model that's representative for the process behavior. Now, if we take a look at this table and we assess the model, we observe that there's problems in the execution of the process for order with ID 1, 2, 5. For example, we observe that after creation of an order, the next thing that happens is the removal of an item. But according to the model, this is not possible because we should have first seen an addition of the item. And in fact, we observe that something is simply missing because after this removal of an item is added, and that's still not possible. Sometimes these problems, they occur because of a faulty execution, but of course it can also be the case that the logging of your data, of your process is simply inaccurate. It's not necessarily the case that people do not execute the process in the right or the intended way. There can also be data quality issues. Another example would be that in sending the invoice, we observe that again, there's no order submitted. So this would be a problematic case if we assume that the model on the bottom is an accurate representation of what we want the process to be. This is important to take into the back of your mind. If you use a different model, you can get very different conformance statistics. Some examples, and I realized I forgot to translate the slides from a German version, so excuse me for that, but in the end, you can use these types of techniques to detect deviations from main behavior. Then in the end, you can also compute the severity of these problems, and you could also try to, in the end, find root causes. So once you know a certain problem is present in a number of executions, you can also try to see whether certain data attributes might correlate to this problem. It could be that a specific type of case is handled in an inaccurate manner. Then we have process enhancement. And process enhancement is a sort of a broad term for all kinds of techniques that in the end try to aim to calculate the ways to improve essentially the process performance explicitly by also exploiting additional data attributes, right? So obviously the example that I've shown you, this was the example table of our shop, is not really a realistic representation of the data that is in the information systems. If I would take a slightly more realistic yet still synthetic sort of example, this would be a more realistic example just to sketch how this type of data would look inside the systems. And what you sort of have to think of in process enhancement is what you try to do is you try to take this data and you try to somehow do something with the model that you have of the process to make in the end, let's say the information you get out of it a bit more valuable. For example, you could think of it as follows. If you have a process model that again describes the behavior that you intend your process to have, you can try to exploit the event data to turn the process like the cake on the left-hand side of this image into in the end, the final cake with the candles and the nice toppings. So you try to enhance models. Right, so for example, we have techniques that enable us to basically project the historical flow of behavior on top of such a model. And we also actually have techniques that can also show you where they then actually deviate from this model. That's not shown here, but it's fairly easy to do. That techniques that allow you to, in a more statistically grounded way, mine bottlenecks, do decision mining. Okay, when are we handling a case in a certain way on average, and why is that? Sometimes that can really augment the business knowledge. In fact, there's also other perspectives like social network mining, etc. So finally, an overview of the 3 different pillars of process mining, and I would finally like to spend a little time in discussing some, let's say, tools, so process mining tools. So what is out there? If you look at my story so far, what is out there in the commercial world, and what is, for example, out there in the open source world, of which I've been a main driver with some other people as well. What are the differences? What are the pros and cons? So when you look at commercial tools, there are various tools, and to be honest, at the moment there's a lot of acquisitions of smaller players by bigger players. So these type of images are usually, when you create them, the next day they are out of actually outdated. So, for example, Lana Labs has been recently acquired, and also Process Diamond, just to give you an example. But most of these commercial solutions, they primarily focus on the process discovery angle, and then they also typically show you this visualization that I've quantified when I was explaining to you the process discovery algorithm. So just this graph where you have connections if one activity is preceding the other activity. That's what they primarily do. So advantages when you use commercial tooling for process mining there's a big number of advantages. So this is super scalable usually. They have, of course, great support, hopefully at least. It's a low-code type of environment, so usually these solutions are plug and play. You don't need to be a programmer or a very experienced data scientist or very technically oriented to be able to use these tools. They are really intended to be very user-friendly and intuitive to use. So those are a few of the many other pros of commercial tools. And of course, if you want to know more, just visit the websites of these different tools and they will tell you all their key differentiators and why they are good tools. There are some downsides as well. And I think the main disadvantage is that for obvious reasons, these tools typically used to show you this process visualization, this directly follows graph, also referred to as a process map, because the reason is that on average, the average user finds that or thinks this is more intuitive to understand than a process model that has all kinds of complicated relationships, also including concurrency and all kinds of choices, etc. And this is, of course, to some degree also easier to interpret, but at the same time, it's very dangerous to assume that such an image, which looks like this complex spaghetti monster, as we often call it, is actually corresponding to a complex process execution. And I will give you an example why this is not the case. But what's typically done in practice is you see the first view of your process and you think this is a complete mess and it's definitely not very optimal, nor streamlined, nor efficient. So you then filter this visualization. You reduce complexity by hiding away the less frequent execution paths of your process to end up with a model that looks more like the ones I've shown you in this slide. And then people say, this is how this process should be executed. This is how it's going to be efficient. Let's try to re-implement, or let's try to structure our organization to execute the process as we see in this filtered visualization of reality. And again, I'm not saying that you shouldn't use these models. I'm saying you should be careful when you do this type of analysis in this way. Why is that the case? If you take one of the most I would say the most optimal or the most highly performing processes that is out there, arguably this is a pit stop of a Formula One car, where time is of the essence. You have to be as fast as you can. Hence, at great resource costs, in a Formula One pit stop, we managed to effectively execute almost everything at the same time. That's what makes this so super fast and super efficient. That's always a trade-off between efficiency and resources and the number of resources that you want to invest. However, if you generate maybe 100 or 1,000 historical pit stops, so you look at event data of, historically speaking, of pit stops, you would see that all these different pit stops, there are going to be slight variations in terms of the completion times of the different activities that are performed, right? So if you would have an event that says dismount the left front wheel and mount the new fresh tire on the left front wheel, you will observe that in a one part of the executions, the left front wheel is mounted first, but there's also a part of the executions where it's mounted last. And the same holds for the right rear wheel and all the other activities, because everything happens at the same time. That doesn't mean that in practice there will be slight variations between the actual time that things are finishing. So there's a lot of variability in this process, and inevitably, and actually we did this in a sort of dummy project, we just literally simulated these type of bit stops with slight variations. If you load that into these tools, you will get pictures like this, because these slight variations make basically a large spaghetti monster of large spaghetti monster, not because the process is inefficient or complex. No, it's a super streamlined, very efficient process. It's because there's slight variabilities in a largely concurrent process. So concurrency naturally generates, if you use this visualization, naturally generates these type of spaghetti monsters. And the danger is if you would filter this into a level that is more digestible and less complex, based on our example data, you would actually get a process visualization that would specify that sending the invoice should precede checking the stock. And this is problematic because if we all together with our company would reorganize our process to be now sequential, so I have to first finish sending the invoice before checking the stock, I'm flattening the concurrency that was originally there. And I'm actually potentially slowing down the process. And the biggest problem is that in these tools, it's not always also so easy to see that you're effectively slowing down the process, which you potentially are. So some questions that you can really easily answer and with these tools is detecting bottleneck activities or activities that go exceedingly slow, ping pong relationships. So, you know, cycles in these graphs typically shows that activities are being repeated, or you can in general also see which activities are slow. What's just simply more difficult to answer, and I wouldn't say this is a point of criticism, is a point of being aware that these things are possible, but not always in the current state of art, is trying to really find common deviation patterns, trying to find activities that are effectively skipped, because this is hard to see in these graphs that I've shown you. Answering questions like how to smartly rearrange activities to be really faster, because as I've tried to show you, this is not always, it will not always be what you think it is. Or more advanced questions where you need some type of causal inference, where you would want to say which investment would lead to increased process performance. So in the end, these tools are great, but they're sometimes also a bit like driving a Ferrari in first gear, where the data allows you to simply do much more than you can get out of it. Now, I don't want to claim that there's a solution for this, and if you would use slightly more advanced tools, you would probably drive the Ferrari in second gear. That's also the truth fact. I don't want to claim that you shouldn't. Anyway, when you look at open source tooling, you see they usually originate from academia and hence have a more broader spectrum of techniques that they cover, because also I think it's a part of the fact that when you come from academia, you simply are aware of that the techniques exist, and there's not necessarily business value that needs to drive the development. However, the downside is that those techniques do require much more technical know-how and skill to operate them, and that's a bit the trade-off. If you look at the open source world, partially open source world, we have the Process Mining Workbench. That's a very old, let's say, academic ecosystem with the UI that can still be used today. Completely open source and free to use, but quite a steep learning curve. Then there's PMTK. That's a more novel recent development that my group launched. That is based on the open source PM4Py framework. So there's an open source Python framework for process mining. That's the one that I founded, and we have also a front-end solution that builds on top of that. The front end itself is not open source because this is merely an engineering type of work, but it's simply using algorithms that come from PM4Py, so that part is open source. As an alternative to Python, if you're more into R, you can also consider the Boopar library, which is made by my Belgian colleagues and people that I sometimes also collaborate with in scientific world. For PMTK, it's worth mentioning that we do consider some form of spin-off there. because we noticed that there is some industry interest in this, and when we go that road, we do want to support the industry partners in a more professional way than we can achieve from a scientific organization. That's just the main reason for this. So we're at the moment looking into that, and we're of course always looking for launching customers. And I do guarantee that at some point we will have more than the process map there. Actually, we already have it, but in a better way. Thank you very much for your attention. And I have so far not been interrupted, but still there's room for questions, I guess.
Definitely. First of all, thank you very much. Really enjoyed the slides that you just presented. Are there questions from the audience?
Excuse me, can I ask one question?
Sure, go ahead.
Yeah, regarding tools and software for business process modeling and business process mining, would you recommend one software tool which we can use in both, which is good to use in both, in business process modeling and process mining?
Well, I cannot like directly say you should use this, because first of all, I'm working for a neutral scientific institute. What I think is important, if you support the need for modeling your business processes in an accurate manner, that you use a modeling language such as BPMN is, I think, the best option. And then there are certain tools that provide support to model BPMN models. You can think of Camunda, you can think of Bonitasoft. I think also Signavio has originated as a BPMN modeler, and there might be more. Again, there's also, I know there's Process Maker. There's also some versions that have less formal models, more, yeah, less, let's say, precise. And then try to pick a solution, a process mining solution that is also able to somehow learn these types of models based on data. I know, for example, there is in Celonis, there is some support for BPMN discovery. It's a bit hidden in the tool or in the software, but it exists. Another example is the Apomore framework, which is also, by the way, an open source based framework, which I could also have mentioned in my final slide, by some of researchers from Australia, which I've also frequently been in contact with and co-published, but they also support BPMN, so that's sort of requirement. For my own research group, we are working on a data-driven process modeling tool. So that's a tool where you can load event data and you can model, and you can assess directly if you have your model. You can assess directly the feedback with respect to your data of your model. You can also let your computer auto-fill the model in a way, so auto-complete the model or compute how to repair your model in the best way for adding additional behavior. So also that would support BPMN. So there's a bunch of different tools out there. But I think if you want to use modeling, I think the modeling language that you want to use should be then your primary driver to then select the two different tools. Thus far, these two worlds are very far apart. And I think that will change gradually. So I think more and more purely business process modeling tools will start to try to integrate data somehow into their value proposition. And I also think that more and more process mining vendors will try to factor in models into their value proposition, because the business will probably ask more and more about predictive type of analytics. And for this, having a model that accurately represents the behavior is simply beneficial for the quality of those predictions in a lot of cases. Not always. There are some neural network-based approaches that don't really require a model, but that's, yeah, I would say not always, not in all cases useful.
All right.
Thank you so much for this, giving such a brief details. Thank you.
We've got more questions. Jonathan, please go ahead.
Yeah, thank you, first of all, Bas, for the nice presentation.
We know each other. We're colleague.
I actually work at Fraunhofer too, but at a different department. So I have a little more technical question, actually, because in one of your recent podcasts in Minding Your Business, I think you briefly mentioned for PM4PY that you want to make it more pandas-like and you want to adjust it more to Python. I would be super interested in a little like heads up, a roadmap, when this is going to happen or when we can expect a bigger launch there.
Yeah, that's a good question. So we are, so from a strategic point of view, we are like, we now have these sort of different representations of the data. And we decided to drop the event log object representation. So everything should be data frames. It does have some implications for the XES certification that we have. So we used to have the full certification. So every type of success log that you put in and you should be also exported in the correct way. We will lose the certification slightly because using this design decision, we no longer support nested attributes, but this is a very technical detail. So that we're working on that in these, but it's quite an intensive workload. And I'm heading a group, so I operationally have limited to no time to work on this. I do sometimes try to work on the documentation, so I expect this to be hopefully before September. At the moment, we're running several courses in the university here, so we won't here internally update this until the courses are passed, because otherwise all students will be very confused when they update their PIP, the PIP list of packages and everything might break, although it will be backward compatible. We're also changing really the documentation. So we're now extending the code to directly pull the documentation from the code with doc strings. Yeah, so that hopefully would also be a bit more intuitive, and that you can easier drill down into really let's say the function characterization, right? Which input objects, output objects, small snippets of examples. But it's just a lot of work, and my colleague and I are mainly doing that, the two of us. And whenever we have time, we do that. But it's an ongoing active branch in our development. So hopefully by September or something, we have a 2.3 release.
Looking forward to it. Thank you.
Yep.
All right, Ivan.
Yeah, thank you very much for your presentation. It was very interesting. I found specifically interesting the comparison you made between the commercial tools and, to be more specific, inductive mining algorithm, right? Because you were talking specifically about this algorithm that somehow mines concurrency. But the approach behind the inductive mining based on the cuts and for the concurrency case specifically, the interleaving analysis, it's kind of weak. So talking about the reliability of the result, we can find a simplified process model as a result of inductive mining algorithm, but it should be less reliable than maybe more complex, but kind of objectively DFG model provided by commercial miners. And I find this, well, not exactly the good reason to say this is better than any commercial miner. So what do you think about it?
Yeah, so I largely agree. Of course, we sometimes do this also to be a bit provocative, right? Why not? You're right in the sense that this concurrent cut actually often you won't observe it so much. So if you would apply inductive mining in practice, the reason why it still finds concurrency is actually because the algorithm also includes a set of I would say if then else statements, although formally we call them fall-throughs, which detect all kinds of potential concurrence constructs. The truth is indeed that the inductive mining algorithm is designed to always describe everything you put into it. And talking in data science oriented terms, this would yield a very imprecise model. This is a fact of life. I'm not against DFG based models. Not at all. I also don't believe fully in automated discovery. I believe in humans supported by computers when they do discovery, because automated discovery is also not at all able to include domain knowledge. So there are examples of publicly available data sets where the first 3 or the first 2 executions that occur most frequently are actually undesired behavior. And you can only filter that out if you know about the context of the process at the same time. So I'm not against these process maps, as they're often called. I would say, and this is a very important point to make, that when you use a process map, that you have to be fully aware of what you can and what you cannot conclude based on the process maps. And this actually, and that's a valid point from your side, this also equally holds for process trees or petri nets that you mine using the inductive mining algorithm. I mean, there you also need to be aware of the fact that these models are usually very, let's say, imprecise, or they describe an additional amount of behavior. And you would, for example, need to do this overlay that I've shown you in one of these enhancement slides to get a better understanding of how this process is actually flowing through that process model network. So I would say, if you know what the limitations of a process map / DFG are, it can be of much more value than a process model that you mine with some algorithm. At the same time, if you misuse it, you can completely come to false conclusions, and that's dangerous if you then want to change your business based on completely false conclusions.
Yeah, thank you.
I think we have time for one more question. Okay. Sebastiaan, thanks again for the very nice presentation, and we had a lot of questions now in the discussion afterwards. Let's discuss if we are able to share the slides on our Discord server.
Yeah, for me it's fine. Yeah.
All right. Then the answer is already there. So check out our Discord server for the slides, and hope to see you in the next e-meetup. See you.